Alright, we want to move into the first really major topic of this second part of electromagnetic radiation. Now, there's a little bit of historical background on this. I'll leave you to read that, but it has to just deal with Hertz's experiment when he used that spark jumping across that gap between the two electrodes and he discovered radio waves. One of the things that Hertz determined, or what he thought, is that if he polished those metal spheres, he found that the receiver worked much better. But it actually wasn't because of that. The polishing had no effect on this. What the actual reason for this is that the UV light produced by the spark was seen much easier by polishing the spheres. It was always there, it's just that polishing allowed it to be seen easier. Hertz didn't actually know anything about this or why it was happening. He also didn't care and didn't investigate it further. We're going to kind of investigate this phenomenon a little bit more detail. So we're looking at this process of bombarding metals with electromagnetic radiation. And what we'd like to do is we'd like to do this with short wavelengths or high energy, because again, we know that energy is proportional to 1 over the wavelength. Now what we'd like to do is we'd like to bombard this metal with energy that's sufficiently high in order to actually get that metal to emit electrons. So this process is known as the photoemission of electrons, or the photoelectric effect. So these electrons that do get emitted, sometimes we do call them photoelectrons. Calling them electrons is just fine. Now, the photoelectric effect, in its discovery, it presented a couple peculiarities that really didn't make a lot of sense, especially through the lens of classical physics. So, first off, the one thing is that electrons were getting energy from this electromagnetic radiation, and eventually that they would break free from the metal almost instantaneously. So, this was the quantum reality. Electromagnetic radiation comes in, electrons liberated essentially instantaneously. From a classical perspective, this doesn't make a lot of sense. We'd kind of think of this like the electromagnetic radiation comes in, the electron starts to oscillate, it starts to vibrate as it gets more energy, it vibrates more and more, and eventually it'll release. Kind of the analogy to that is like if you're boiling a pot of water. What the quantum mechanic interpretation of this is that the moment you turn on the burner, the water boils instantaneously. Whereas what we are used to is, if you turn on the burner, it takes a little bit while. It takes some time for that heat to transfer. And then, we have that oscillatory motion of those water molecules, and they vibrate and vibrate and vibrate. And then eventually it starts to boil. So that was the first peculiarity. This instantaneous ejection of the electron didn't really make a lot of sense. The other real peculiar thing is that there was a minimum frequency required of the electromagnetic radiation that was incoming in order for the electron to actually be liberated. And this frequency is what we call the threshold frequency. So we denote that by F0. If the incoming radiation had frequency less than this, no electron was going to be emitted. If the frequency was at least the threshold frequency or greater, we would have an electron being emitted. So this was another peculiarity. The last one, and we'll discuss this one in a bit more depth later, if we change the brightness or the intensity of the light, it doesn't actually have an effect on the kinetic energy of the individual electrons being emitted from the metal. That also really flies in the face of what we have learned from a classical perspective, but we'll also talk about that one a little bit more later. So the photoelectric effect introduces a lot of peculiarities, but we want to investigate those peculiarities because, as I mentioned earlier, those are the bases for modern physics. So Einstein's contribution to this is that he extended Planck's idea of quantization. So Planck basically stated that energy is quantized. Einstein took it a step further and said that light itself is also quantized. Now, what we've said is that in order for the photoelectric effect to occur with the photoemission of electrons, there has to be a minimum frequency of the electromagnetic radiation for that to happen. So what this also states is that if there's a minimum value of frequency, there's also going to be a minimum value of energy. So this minimum value of energy, in order to liberate electrons from a metal surface, this is known as the work function of that metal. The work function the work function's formula is this H times F0. So W is our work function, H is Planck's constant, F0 is that threshold frequency. Similar to using Planck's equation, the work function and Planck's constant, we have some liberty with the units. We can either use joules for the energy and joule seconds for Planck's constant, or we can use electron volts for the work function and electron volt seconds for Planck's constant. But the main thing is they have to go together. If you're going to use joules for one, you got to use joule seconds for the other, and vice versa. If you're going to use electron volts for one, you got to use electron volt seconds for the other, and vice versa. So essentially, our conditions for photoemission to occur is that energy of the incident radiation coming in, it has to be greater than or equal to the work function, because the work function represents the absolute minimum amount of energy required to liberate the electron. If your energy is less than the work function, well, you will not liberate any electron, and so we would say photoemission does not occur. So 1905 is when Einstein proposed the photoelectric effect, and 1905 was a really good year for him because he also proposed his theory of special relativity that year. Einstein's contributions to the photoelectric effect actually won him the Nobel Prize in 1921. A lot of people thought it was for his work on special relativity, but that's not quite the case.